Friends, let us continue with the 11th lecture in module 1. Here we will discuss another example problem of orthogonal structures planar. Before we move on to the general principle applied to problem 3, let us quickly revisit what we have seen in the last example. The last example is actually a single base single story frame, as you see in the figure here. There are 3 members A, B, B, C and C, D of different EI values subjected to variety of loads on the span A, B, B, C and C, D. If you look at the results, what we have obtained, we obtained the stiffness matrix for the member A, B, stiffness matrix for the member B, C and stiffness matrix for the member C, D, considering fixed beam as a standard model. For example, while deriving the stiffness matrix for A, B, the labels were theta 1, theta 3, delta 9 and delta 4. This is simple to a fixed beam of P, Q, R and S. So, 2 rotations and 2 translations where this is my x axis and this is my y axis. So, for every member I have to orient the axis and accordingly I must select the label. Similarly, for KBC we should have labels as theta 1, theta 2 and delta 5 and delta 8. For KCD the labels are going to be theta 2, theta 6, delta 9 and delta 7. So, the whole derivation we have neglected axial deformation. Friends, it is because of this reason you will see delta 9 and delta 9 are same at the points B and C. Similarly, delta 5 is same at the points at the nodes A and B. By the same reason, delta 8 is same at the nodes D and C. So, amongst this we very well know that theta 1 and theta 2 are unrestrained degrees, and remaining theta 3 through delta 9 are restrained degrees. So, we formed the stiffness matrix with U and R. We partition the stiffness matrix. The total matrix is 9 by 9. We partitioned it with 2 by 2 and further. Then we also partition the displacements delta U as theta 1 and theta 2 and delta restraint will be actually the remaining theta 3 onwards, which is actually 0 because all are restrained degrees of freedom. We obtain delta U by inverting KUU. We use this relationship KUU into delta U is actually equal to JLU. We found out delta U by inverting this matrix and we got delta U. Then we found out fixed end moments in end reaction of every beam using this relationship, fixed end moments of the ith member. So, the final solution what we had looked like this. This is subjected to a UDL of 12 kilonewton per meter for a span of 6 meters. Which is AB. Similarly, for BC we had a point load of 50 kilonewton which is equally spaced, and this distance is 4 meters, and for CD we had again loads which are 20 kilonewton and 30 kilonewton which are equally spaced. In addition, we also had joint moments here as 20 and here as 30. So, for this we found out the results. The results are as follows. This reaction end moment is 39.759 and this is 28.487, and this reaction was 34.123 and this value was 37.877, and for this beam this reaction was 48.487 and this was 13.519 and this became 16.479 and this became 59.369. This reaction was 40.502 and this reaction is 9.498 and this reaction is 11.444 and this reaction shear is 38.556. So, one can apply a check and see. Let us take the span AB. So, let us say sigma FH should be 0. So, one can see here 12 into 6 is actually equal to 34.123 plus 37.877. Sigma MA, let us try to find out, which is going to be plus 28.487 plus 12 into 6 into 3 minus 34.123 into 6, which will be counterclockwise of 39.75, which is as same as this value. If you look at span BC, sigma Fy should be set to 0. So, 40.502 plus 9.498 amounts to 50. Similarly, want to compute MB will be actually equal to minus 13.519 minus 9.498 into 4 plus 50 into 2, which amounts to anti-clockwise of 48.489, which is same as this. In addition, you can see the net moment at joint B is 20 and the net moment at joint C is 30. So, by this logic one can check the section CD. I leave it to you, check for any error in the solution. So, let us try to find a general summary what we have so far applied to these two problems. So, the first step is identify unrestrained and restrained degrees of freedom, essentially displacements. They can be translational, rotational. but please note first set of labels will be unrestrained, the second set of labels will be restrained. This is required if we really want to partition the matrix for analysis. The second step was to determine the stiffness matrix of every member, fixed beam, neglecting axial deformation is considered. Xm and Ym of the ith member is chosen to identify the labels of stiffness matrix of the ith member. So, once K I of all the members are joined and found out, then we partition the K matrix of the entire system and obtain only K unrestrained matrix, then invert this matrix. From the fixed end moment, we need to identify the joint load vector. Joint load vector is nothing but reverse the sign of fixed end moment and identify the joint vector. The joint load matrix is also partitioned as unrestrained and restrained, then K unrestrained with joint load unrestrained is K unrestrained with displacement unrestrained is joint load unrestrained. So, then we obtain delta u, which is actually K u inverse of joint load unrestrained. So, we can get unrestrained displacements, and friends, we all now remember the restrained displacement will be 0. Okay. Then we identified the end moments and end reactions of each member by using this algorithm K I delta I plus fixed end moments of the ith member, and found out the mi vector for every member, and then one can check this solution also with the following relationship. K R u delta u minus J L R should be actually also equal to the reaction R. So, substitute this, examine the results obtained from the previous steps and then compare and validate. So, interestingly friends, in this case the method proposed, which is actually the stiffness method, does not depend on the type or geometry of the problem, it is independent of the type of load, the procedure applied is generic, it has got repetitive steps and therefore easily programmable. Let us apply this for another problem. In fact, we will not solve this problem, but we will see how solution can be obtained for this problem. So, this is example 3, which is slightly a complicated problem. Let us say I have a frame like this, which is fixed at both the ends. Okay. Now, the moment of inertia of the column section and the beam sections are marked as shown in the screen. Let us also name the joints A, B, C, D, E and F. Let us see the loading applied to the system. There is a joint load here, which is about 20 kilonewton. There is a joint load here, which is about 30 kilonewton. That is all. There are no member loads, that are directly applied on the joints. So, what is the first step? The first step is identify unrestrained and restrained displacements at each node, is it not? Let us do that. Let us mark unrestrained in green and restrained in red. So, this is theta 1, theta 2, theta 3, theta 4, delta phi. Since the delta phi is same at nodes B and C, we can say that axial deformations are neglected. So, delta phi, then delta 6, then delta 7, then we have theta 8, delta 9 and delta 10, theta 11, delta 12 and delta 13. So, now friends, there are 13 degrees of freedom. Let us now say what are unrestrained degrees. We can name them theta 1, theta 2, theta 3, theta 4, delta phi, delta 6 and delta 7. What are the restrained degrees of freedom? We can name them theta 8, delta 9, delta 10, theta 11, delta 12, delta 13. So, that makes total 30 degrees, out of which 7 are unrestrained, the remaining 6 are restrained. Okay. So, there is no difficulty in doing the first step, which is identifying these degrees of freedom. Okay. The next step is for a member, this is step number 2. Let us identify what should be the jth end and kth end, that is orientation of the member, and what are the degrees of freedom labels. Okay. Let us take for example BA. The moment I say this is the orientation, so this is going to be my xm and ym for BA. So, I should write here BA, jth end is at B, okay. Kth end is at A, and what are the degrees of freedom? Compare this with the standard fixed beam. Okay. Let us say the fixed beam is marked parallel. for our understanding. Okay. Let us call this as theta p, this as theta q, this as delta r and delta s. That is the standard beam we have, neglecting axial deformation. So, what are the labels compared to that as far as the member B A is concerned? So, theta 1, theta 8, delta 5 and delta 9. Okay. So, let us do that. So, the labels are theta 1, theta 8, delta 5 and delta 9. Similarly, let us do for the member B C. So, the B C will get aligned this way, this is x m and this is going to be my y m, right. So, jth end is at B and kth end is at C. So, for the member B C, jth end is at B and this is at C. Let us see what are the labels. So, as you correctly pointed out, rotation left, rotation right, normal displacement left, normal displacement right. So, theta 1, theta 2 and this is delta 10 and this is delta 6. So, that is right. So, let us write down that theta 1, theta 2, delta 10 and delta 6. Let us do it for C D. So, C D will be oriented in this fashion. So, this is going to be my x I, this is going to be my y I. So, the labels are going to be theta 2, theta 3, delta 5 and delta 7. So, for the member C D, C is the jth end and D is the kth end and the labels are theta 2, theta 3, delta 5 and delta 7, correct. Theta 2, theta 3, delta 5 and delta 7. Okay. Let us do for the member D E. This is the orientation which is x m and this is y m. So, D and E, theta 3, theta 4 and delta 6 and 13, correct. So, let us do that here. So, for the member D E, D and E are the ends and the labels are theta 3, theta 4, delta 6 and delta 13. You can see here theta 3, theta 4, delta 6 and delta 13. Then for the member E F, let us do the orientation for E F. E is the jth end and F is the kth end and the labels are rotation at J, rotation at K, displacement at J, displacement at K. So, 4, 11, 7, 12, correct. So, 4, 11, 7 and 12. Okay. Thetas are rotations and deltas are translations. So, this is step number 2. So, there is no confusion in step number 2, we can do it for this problem, correct. Let us go to the next step. So, step number 3.